All right, here we go. This is Horner again, and we're going to look at this is the third problem in the Connected Objects Notes packet. We have two masses, M1 and M2, and they're both sitting there, and we want to know what is the coefficient of static friction which keeps the block stationary. So there's got to be enough friction on this block that this block can't pull it down. So one of the things definitely that we have here is we have the force of static friction going to the left. We know that for this one we also have tension going to the right. Going straight up will be the normal force for this block, and then going straight down should be M1G. For this block, going straight down will be M2G, and going straight up for this block will be tension again. If you remember, we like to try to draw these so that they're all kind of going in one direction. So let's go ahead and put that force of static friction on that first block, M1. We're going to go ahead and draw our normal force just like we normally have. M1G pointing straight down, and then pointing to the right is tension. Now I'm taking this diagram and I'm going to rotate everything up 90 degrees, so I'm going to turn it counterclockwise 90 degrees. So here's tension, that's this same thing here. Here's the box, and going in the opposite direction to tension, you'll notice is M2G. And so that's what we'll put here, M2G. Up will be Y and positive, and to the right will be positive X. So let's think about this box. So we're going to look at box 1. We're going to say sum of the forces in the Y direction for that first box will be equal to 0, because remember it's resting on the table, so there's no acceleration. Going up for this one is the normal force. Going down is M1G, and that's equal to 0, so the normal force then is equal to M1G. That's going to be important later. Let's look at the sum of the forces in the x direction for box 1 and the sum of the forces in the x direction for box 2. So here's our mass 1 and box 1, mass 2, box 2. And we know that both of them are at rest, and so those are both 0. Going to the right for the first box is tension. We're going to subtract off the force of static friction, and that should be equal to 0. So the tension here is equal to the force of static friction. Same thing for this side. We'll do everything in the x. We're going to say M2G going to the right minus T is equal to 0. So for this one, M2G is equal to T. Let's go ahead and substitute in this Fs since it's equal to T over here. So I'm going to draw just a blue circle just so we know what we're doing. We're going to put it in right there. And now let's go back and actually do it. We're going to say M2G is equal to the force of static friction. Let's go back and really think about friction. Remember the force of friction, so for us it's static friction is equal to the coefficient of static friction times the normal force. Now remember we said that the normal force, if we go back over here, is M1G. So let's circle this one in green. And we'll draw a line coming over, and that's what we're going to do is put that static friction in right there. So here the force of static friction is equal to mu s times, and remember we want M1G. M1G. So now we're going to take this and plug it in for the force of static friction. So you'll see here's force of static friction. So let's do yellow. And we know that this is the force of static friction. We're going to plug it in here. So let's go back. We'll say M2G is equal to, remember we're going to use this now, mu s times M1G. Now it's pretty easy. We just need to solve for mu s. So mu s is equal to M2G over M1G. And you'll notice the g's cross off. So now we're left with M2. Remember mass 2 is a 5 kilogram block. So this is 5. And the other block, which is block 1, is 10. And so our mu s, or our coefficient, here is just 0.5. Remember, there's no units for that. And that is the end of the third example problem.